All right. Hello, everyone. My name is Krister Shalm, and welcome to this week's edition of our ASPEN-Net quantum tutorial series. And so today we've actually got two different tutorials. One is going to be given by myself on path-entangled sources for path-entangled quantum networks. And our second tutorial following will be given by Nick Nardelli, who is a postdoc here at NIST and specializes in phase stabilization technologies and how you would actually phase stabilize a path-entangled network. And so, as always, please feel free to interrupt with questions or put questions in the chat, and one of us will ask it on your behalf. So this is meant to be a little more interactive. I want to mention that today's tutorials will probably be a little bit more technical in some areas than some of the other tutorials. We're going to get into some of the more nitty-gritty details that have been kind of requested. So just be prepared for that. And this will also be recorded and shared on our website, quantum-aspen.net. The previous tutorials should also be there as well. And just kind of one other housekeeping note is that coming up soon on June 1st, as part of or connected to the Optica Quantum 2.0 conference, our team will be holding a town hall to kind of gather, user feedback and community feedback, and search for additional collaborators for this kind of upcoming NSF National Quantum Virtual Lab project. So there's still some spots available. So if you want to register, you still have time to do that. Okay. So our project is really based around this process of our approaches based around single photons generated from the process of spontaneous parametric down conversion. And what we're going to do is for SBDC, it's a process that's um, sorry, Zoom keeps taking over my screen. So spontaneous parametric down conversion is a process where you send a pump photon in, you undergo kind of a nonlinear process, and you can then generate pairs of photons that will happen spontaneously. And the probability of this happening is quite small. So, um, oftentimes materials can be like 1 in 10 to the 8 or 10 to the 10 pump photons will down convert into the signal and idler. Fortunately, pump photons are cheap, so you can actually make fairly bright sources with this approach. And if you're phase matching, what that really means is that the phase velocity of the signal and idler and pump photons all need to kind of propagate at the same velocity through the crystal. And as long as energy and momentum are matched through this process, and you can design your crystal properties to do that, then down conversion is supported. And you get out a wave function where the photons in the signal and idler have strong correlations with one another. They're born at the same time, and often will come out in this kind of sync profile. And we'll talk about that a little bit later. So this is going to be the workhorse for our approach. Now, it's hard to actually talk about a quantum network and what you need in a source without first really diving into, what are the parameters that are required in your source? Like, what are you going to use this network for? And different network applications are going to lead to very different uh, source requirements. So if you wanted to do just, quantum key distribution, that's going to be very different than if you want to build a quantum repeater. And so in our network, we're really targeting quantum sensing, quantum communications, and eventually connecting to quantum processors. But the first real application that we want to go after that's going to have I'd say, a quantum advantage, at least one of them, is performing these loophole-free bell tests. If you can perform a loophole-free bell test, which involves distributing entanglement to two remote nodes, and then performing operations on those measurements on those qubits, um, you can violate what's called a bell test. And these have been very foundational experiments in quantum information science, and they have pretty stringent requirements. You need to generate very high quality entanglement, and you can't have much loss in your system. Like if you have if you lose more than a third of your photons, these experiments just aren't even possible. And so our team at NIST has been doing these experiments with polarization entangled photons based on down conversion. We have very efficient detectors, and we've been doing a lot of work on kind of building these setups. And you can actually use a loophole-free bell test as a kind of building block for doing a lot of other things. And in particular, these so-called device-independent quantum communication protocols, where you can actually use a bell test as a kind of building block to exclude, quantum adversaries or show that you have, true randomness. And we've been doing a lot of work on these device-independent protocols. And here's some examples and references for folks to look up. We've even launched a new service, which is the CU randomness beacon, where you can actually create traceable quantum randomness. And so that paper will be coming out soon. And these protocols need some pretty stringent performance requirements. So here's an example of a plot that my graduate student Gautam Kavori put together. And it just shows, how often or how long do you need to run your experiment to get out 512 bits of randomness, this device-independent randomness, as a function of your system efficiency. So, if I produce a photon, how often do I detect it after going through, my fiber and all the fiber coupling stages and all the other options? And it's an exponential kind of curve. And so you end up with, if you look here, when we first did our experiments in 2015 with the initial Bell test, at about 74.5% efficiency, it would take about a day of running this experiment to collect enough statistics and data to actually be able to, perform this device-independent protocol to the level we want. We improved by 2% for the next iteration, up to about 76.5%. And that dropped our runtime from 1 day to 10 minutes. And in our current experiments over this network, we're now up into the kind of low 82, 83% level of efficiency. And now that's already dropped a further 20 to 20 seconds. And so if you have a system that is lossy, that can really affect the quality or the runtime of your experiments. And so you never want to be right on the edge of efficiency bounds. You want to be well above that in order to actually carry out these experiments. And if I were to do something like, instead of system efficiency, if this was, say, the fidelity of my entangled state or the quality of my entangled state, you get something kind of similar. So a lot of quantum networking efforts right now, people are showing that they can just get above maybe some of these bounds of quality required, but that's not really necessarily useful entanglement in the current state, because if you have to run your protocol for days or months or years to get anything out, you can't really do much. So really, our goal is to try to develop high quality, high efficiency, high fidelity entanglement in a quantum network, so we can actually do useful things. And one of the options would be, well, if I wanted to take this experiment that's at NIST, and we've got our two sources separated by 93 meters, and I now want it to go into a city, there's going to be too much loss in that fiber, and we need to overcome that. And so if I just took our polarization entangled photon sources and made two of them, well, then I could do entanglement swapping in principle, where I send one of the photons over the fiber link from each source to a central kind of node, where you then perform entanglement swapping to get the right click pattern in your Bell state measurement here in the center. Then what you end up with is swapping in polarization or time bin entanglement or some other kind of entanglement beat where each side gets one photon. The problem with these sources is that you're just as likely, instead of getting one photon pair at each side, I'm just as likely to either produce two photon pairs on this side or two photon pairs on this side. It's a probabilistic system. And this introduces unavoidable errors, errors that we cannot correct. And so you just can't build a scalable quantum network with this approach, unless you were to put in some other device here that could tell you, when filter out like these higher order paraemission events or do something else, you need some strong nonlinearity for that to happen. So um, we need something different. And this is really what's led us to ASPEN-Net, because these kind of pair sources and really trying to use this two-mode entanglement where you've got each party gets a qubit just isn't going to scale. And so, for any kind of quantum network, you really need to know when things happen. So our approach is instead to look back to the original scheme. And again, Mike Mazurek talked a lot about this in a previous tutorial, so I'm going to go through this kind of quickly. So if you want a more detailed look, refer back to his tutorial on that. But we're really basing it on this, what's called DLCZ protocol from Dwan, Lukin, Serac, and Zoller, and showed how to build a quantum repeater using photons and atoms or matter-based qubits. Now, a version of the DLCZ protocol, and I'm going to go through kind of like of the basics, of how you would do, say, a Bell state measurement, because that was asked for by some folks in previous iteration of the tutorials. I'll just go through that briefly. But really what you can do is you can start with a single photon now, and you can send it to a beam splitter. And you don't know which path the beam splitter went in, A or B, and that generates what's called a path-entangled state. Now, in the original DLCZ protocol, you can actually, if you had transduction, for example, you could couple that photon to these atoms. And that would leave you in this ground excited plus excited ground state. And now you can actually go about and do your quantum operations. Transduction is really hard. And I would say it's not a problem that has been generally solved yet. So instead, what we're going to do, one thing that you could do is, instead of coupling to atoms, if you want to measure the photons, the photons, like those relative paths, the qubits encoded by these relative paths, you could instead bring these paths back together and interfere them with one another. And by changing the relative phase of the two paths, you could get various measurements of like kind of qubit measurements. But if you look closely at this, there's a few flaws in this scheme. The first is, well, this is just a Mach-Zehnder interferometer, and those have been around since the 1800s, I believe, before quantum mechanics was even developed. And the second is, I guess the more fatal flaw is that when you bring these paths back together, that really isn't conducive to a quantum network, because what you're doing is you're sending your qubits out, and then you have to bring them back to the same lab to be measured. So you can't really do remote operations. Instead, another alternative, instead of just measuring the relative phase that's accumulated between these two paths, and by bringing the two paths back together to compare them, you could instead inject a local oscillator into that output port of the Mach-Zehnder and distribute a coherent state to each path that acts as a stable phase reference. So instead of bringing the photons together, you bring the phase reference to these remote photons, and then you can actually do measurements remotely. By modulating the amplitude and phase, you can create different weak local oscillators that act as a phase reference, and you can do a weak field homodyne type measurement. So in our protocol, we're trying to build up to a system where you don't even, as long as these local oscillators, alpha and beta, they don't even have to be derived from the same source. As long as they are synchronized and share a stable phase reference, you can use them to perform your quantum measurements. So in our experiments, these weak field homodyne measurements, you bring your single photon into a highly transmissive beam splitter, so there's very, very little loss. You mix in this weak field homodyne measurement, perform this weak field homodyne measurement by mixing in this coherent state. That does a displacement measurement. And what you end up doing is, if you don't detect a click here, that's actually equivalent to projecting onto a coherent state. And you can actually go about and do these measurements, like kind of qubit projectors. Now, these measurements aren't perfect. So if you were to do a CHSH test, With the ideal projectors, then you'd be able to get a Bell violation of 2√2. With the ones that you can do for this version here, it's more like 2.69. And your minimum efficiency is actually going to increase to about 84%. So that's quite a big jump from the 66%. And one of the things that's there's some other measurement schemes that are more complex I'm not going to go into, but you could lower these bounds a little bit, but you need a pretty efficient source for this to succeed. So what I wanted to mention is in our scheme, what we're planning on doing for ASPEN-Net is using a single photon source that is um, generated by this process of down conversion. We're going to use a detector to herald that, and hopefully that will have some number resolution. And Marty Stevens talked last tutorial series about how these detectors work. We produce our photons, and then what we should be able to do is entangle these two different paths together. We can store one of those paths in memory that go over these lossy fibers and synchronize the operation so that when both sources have produced photons, we can release them. And then if we get a heralding event, a single click in the middle, then we can generate our photons. We can do our measurements on our qubits at the end. And so some of these paths can have loss, especially the ones that go over the fiber and go into the memory. But the photons that are kept in your lab, those, in order to do these measurements, have to have very high efficiency. So from the time you produce your photon to the possibility of it getting coupled into this fiber and detected by your detector over here, you have to be above 84% efficiency. What we really need is a single photon source that we know with high probability when we've produced a photon, and then we capture that photon and we can get that and do our operations. So a really promising technology for doing this alternative compared to down conversion are quantum dots. But unfortunately, every time you produce or get a signal that you produced a photon from a quantum dot, the best kind of results to date only really couple that in with about 57% or 71%. So there's still quite a bit of work to be done, but quantum dots might be a viable future route for sources. But for now, our kind of best bet is down conversion. And what we really want to do is get above 90% detector like system efficiency for these targets. So that's one of the big driving motivators for our sources. And we've been actually able to do this or approach this with a previous generation of our sources. And I think we can actually do better than this. But in our current sources, um, in just a single lab on a tabletop, we're able to measure system efficiencies that approach 90%. And that's in part because we've these detectors we've developed that have extremely high efficiency, and we've worked a lot on our fiber coupling and other kinds of technologies related to that. So if you wanted to take a down conversion source and create a high efficiency coupling, one of the dominant parameters is the focusing of your pump, signal, and the idler and the crystal. And it's a complicated kind of relationship between those. I ended up working with Alfred Duran, Karina Gary, and programmer Jasper Palfrey. And what we've been able to do is create this program called SBD Calc. You can go to it at app.sbdcalc.org. And you can compute all of the parameters that I'm talking about now. And we use this to design all of our sources. And it's a very accurate simulation of lots of different things that you'd care about. So this is kind of our workhorse for source development. So focusing parameters, you can make plots like this. Here you can say is, how tightly am I focusing my pump into the crystal? So on the left-hand side, that's like a 20 micron waist versus all the way up to a 200 micron waist. And on the y-axis is how tightly am I focusing my collection for my signal and idler? And you get these kind of contour curves where, up here is where we kind of operate currently, our loophole-free Bell tests, where, really trying to get high efficiency. But the trade-off is, you're not going to be very bright. So there's this kind of trade-off here where this region down here, you could be like 12 to 14 times more counts or generate more pairs per second in this regime compared to up in that other regime. But your efficiencies might be like in the 30–40% range, your heralding efficiencies. Whereas you can be much less efficient here, much less bright here, but your optimal efficiency might be higher. You might get like 97–98% overlap with like a single mode fiber from what comes out of the down conversion. And so there's this trade-off. And for every pump focus, this curve here represents what's the corresponding collection waste that would give you the optimal brightness, and that follows one curve. And the other curve is the optimal kind of efficiency. And so SPDCalc can help you design all of that if you really want to build a source based on down conversion. I'm going to also mention that another really important parameter that we care about is what we call separability or indistinguishability. So if you produce a pair, like one of these heralded photons, I need to make sure that if I get a click at this detector here, that spell state measurement, I can't tell if it came from the source on the left or the source from the right. And to do that, you really need to make your photons indistinguishable. So they have to be identical in every way possible so that you get this interference. Additionally, I need my single photons to come in and interfere with a local oscillator photon. And that has to have very high overlap as well. And unfortunately, down conversion natively just doesn't do a very good job of this. This is one of the Achilles heels of down conversion, at least it has been in the past, but we have ways of solving it. And the issue is that when I produce photons from SPDC, they come out highly entangled with one another. There's a lot of frequency correlations and timing correlations. And when you measure one photon of that pair, what you're doing is you project and leave the other photon in a mixed state. And then that mixed state, it doesn't interfere with anything. It doesn't interfere with your local oscillator. It introduces distinguishing information that you can tell, which side a source came from. So you really need to work hard to get rid of that. And so as an example, down conversion on the left, a lot of sources, and when you design them, you're going to get this very strong correlation between the wavelength of your signal photon and idler photon. And so if I detect a photon, my detector is going to project my photon into a particular wavelength. And then that's going to it's going to measure it in a particular wavelength, and that's going to project my idler photon into some other corresponding wavelength. And this is what, you kind of get this mixture. What you really want is a source that is unentangled and separable so that the signal and idler are completely, if I measure the signal, I have no idea what the idler wavelength is. And so when you're designing sources, we have something, as a parameter we use, which is called the Schmidt number, which is you do a singular value decomposition on those kind of the wave function. That's the joint spectral wave function that I just showed. And this K parameter, it tells you the decomposition of how many joint terms you would need to represent this. And so for a Schmidt number of 1, that's ideal. It means that there's only, you can take two functions, a function that represents the signal, function that represents the idler, multiply those together, and you get this kind of joint, it represents this entire spectrum. So, and therefore it's separable. You can decompose it into just two functions multiplied together, one for the signal, one for the idler. So this is an example of a source that's pretty good. It's got very little entangled kind of contributions to it. So in down conversion, you really want to get to this kind of joint spectrum where you've got this nice separable kind of shape. And so one thing we can do is quasi-phase matching, where you can take a crystalline material and instead of just, being stuck with like by changing the optic axis of the material itself, you can actually have your light co-propagate. This allows you to make really long crystals, and by alternating the sign of the kind of effective nonlinearity periodically, you can actually make up for any kind of phase mismatch. So the crystal kind of kicks in and helps out a little bit. So this is a very common technique. I'm not going to spend too much time on it, but um, one of the big problems is for adding like residual kind of making high efficiency sources that um, are really indistinguishable. You want to get rid of this kind of sink term here. And where the sink term comes from is that if I'm sending my pump into a one of these crystals, then in time, what it looks like is, my pump comes in and then suddenly hits this crystal interface, and I have I turn on the nonlinearity. And then that nonlinearity stays on, and then it exits the crystal and the nonlinearity turns off. So in time, I have a square, and you take the Fourier transform of that in the frequency domain, you get a sinc function. So what we really need to do is something where by changing this polling period as we kind of move along, you actually can instead, you kind of do crappy phase matching at the beginning and the end. You slowly turn on the nonlinearity, and you can actually kind of approximate pretty well a Gaussian profile. And that produces photons that are also like have this kind of Gaussian spectrum and are much easier to be separable. So we've got some nice results recently where we've been designing these sources where you've really tried to do this phase matching well, and very, very good separability. And we've also been doing some Hung-Mandel measurements where you take this is the kind of approximating what you'd see with two different sources. And we think we should be able to get above 96% without any filtering for two independent sources. We don't have time to go into this too much. We also have measurements for the local oscillator, where if you take a local oscillator and interfere, we're right now around 87% visibility, but we just need to do a little bit better filtering on our local oscillator to get that up. Okay. So I'm almost out of time, but I wanted to mention that, there is some light filtering that you can do on the Herald photons, on the Bell state measurement photons, and on the coherent state that you send in to do your local oscillator in order to really try to get these visibilities up above 99%. We think we can do that. You just don't want to filter the kind of pristine path and introduce loss into it. So I'm just going to wrap up and hand it over to Nick here in a second. And I just want to mention that, the last major challenge, and this kind of sets up a lot of what Nick will be talking about, is for our system, it needs to be very well vertically integrated. And because this protocol is phase sensitive, we really wanted a system that, you could derive a local oscillator and your down conversion from the same kind of initial system. So we produce a 1550 laser, we double it using second harmonic generation. We then down convert with SPDC, and then we can use that same pump light to make our local oscillator. And when you start to look at like the phase stabilization requirements, especially in the more general case, you need to be able to synchronize and stabilize this pump laser that produces the local oscillator with any kind of cavities or memories you might have, and as well as like stabilizing all the path lengths of this giant interferometer. And so we've had to build systems from the ground up, and we've been really relying on the kind of technologies that Nick's been building, where we can take these lasers that are used for clock comparisons, we can amplify this up. And so our postdoc Michael Grayson's been working a lot on this, and do down conversion, do double that light, and then produce kind of our sources of SPDC, and do all that very efficiently. So Nick's been working a lot on that. He's going to tell us some of those kind of techniques and technologies. Just before I kind of move on, I wanted to just say, is there any questions from folks?
Yeah, I have a question. Can you hear me?
Yep, I can
Oh,
hear you,
great.
James.
Okay. On your previous slide before this nice picture of the team, yeah, that guy right there. This coherent alpha or the coherent beta waves come in. Are they harvested then at some point? Do they have some information on them that you're going to use?
So we harvested the local oscillator here, and right before we send in the 775 component, there's 1550 and 775 light in our system. We harvest it. I don't know if you were here for the beginning, but like our measurement
Yeah.
scheme requires, I talked a little bit about how you use that local oscillator to make a weak field homodyne measurement. That's a displacement measurement. And so by modulating and changing the amplitude and phase of this local oscillator, you can actually make your measurements directly on your photon, but you need it to have the same properties. It has to be indistinguishable from the downconverted photons that you've produced.
So it looks like here you've got a lot of detectors. Do you um, have an output of this system that then provides you with the two entangled photon states, maybe living on a carrier wave here, or is that not what you're doing? I'm just a little confused about where this is all headed.
So did you, I just want to ask, did you see the beginning of the talk where we
Yeah,
talked
I
about like
did.
the devices?
Yeah,
Okay, great.
yeah.
So the goal is to really come back and in the context of being able to do these device independent protocols, what you need to do is distribute entanglement between two different end stations. And you can just immediately measure that entanglement. You can do these Bell state measurements. That allows you to do these device independent protocols, which have a quantum communications advantage. And so we've got a couple of we got a tutorial, I think, in a month about some of those protocols and going into more detail. So what's nice is you can just immediately measure your local qubits of these arms, and those correlations build up. That allows you to carry out these protocols. And there's a bunch of strict requirements for what needs to happen. So in our particular case, instead of, transducing and coupling the photons directly to an atom, we're just going to use a local oscillator to do our projective measurements and use them up immediately. We don't
And
need to store them.
if you wanted to use them, you could take these detectors out, the two black detectors,
Mhm.
and then send the beam out. Okay, I see. I
Exactly.
missed
So
the
you
fact you were
could,
detecting it too.
yeah.
Yeah.
And you can kind of see that here, where when we herald, I've taken the detector out of and replaced it with this memory and this fiber, and then we can send it off and do, say, a Bell state measurement, or you could do other things with it.
Okay. All right. Thanks.
Yeah, that's a great question. Thanks. Um, okay, I'm going to stop sharing here and turn this over to Nick. And if folks have questions, please feel free to ask them in the chat, and I can respond in the chat too.
Yeah. I am sharing now, right? Continue to share. Yes. Can you all see this? Great.
Yes. Yep.
Excellent. Yeah, hi. So yeah, Krister mentioned me in the beginning. So I'm Nick Nardelli. I work at NIST, and I'm from like this phase stabilization like kind of background. So like I've worked heavily building these optical clock systems and networks in the Boulder area. So our bread and butter is taking these signals that we generate for probing like atomic systems, these really amazing like high quality lasers, and then distributing them across the network, comparing them, and kind of doing all of the stuff that each stage requires multiple phase stabilization uh, steps. So yeah, so anyway, so there's lots of phase stabilization in my background. We're hoping to kind of use it all for this quantum stuff. Next slide. Okay, so Yeah, and kind of in the Boulder area, like I guess, if we're especially if we're using these path entangled states, we're gonna require basically most of the same technologies that we've developed, over decades for clock, making very accurate clock signals and, including, these frequency combs to generate single photon uh, states, these very stable network fibers over kilometers, and then, things like memories and phase stabilized optical cavities. Um, okay, so, and by the way, this is going to be I have some very detail heavy slides here, so don't be afraid to just interrupt and ask questions. That's kind of the point. Um, okay, so do I have time? So yeah, there are kind of a bunch of interesting things you can do if you have like phase stable path lengths. So in our case, we're building up this quantum network based on path entangled states that requires a very high level of phase stabilization. But there are there are a bunch of other quantum, technologies that people are building up, like these, twin field quantum key distribution uh, systems, or these long baseline interferometry systems for things like astronomical observations, and really these things only work if uh, anything that kind of relies on this first order interference of these photons needs phase stable links. Um, and I mean, that's hard, right? Because like an optical wavelength is, a few micrometers, or it's a few microns. And so it's very easy to mess that up. The environment has plenty of noise that can couple to the phase. Um, and so I kind of put a few examples, like people are starting to get interested in phase stabilization for a lot of these systems. And to me, when I read, some of these papers and kind of see the results, I don't really know what they're doing. Like I feel like there's not a good standard for, what is a phase measurement and like what constitutes a good phase measurement. And actually, how do you actually stabilize in like a good way, like optical fiber paths and even free space paths and other things. So yeah, like in these two cases, for this kind of quantum key distribution example, they're showing maybe 470 milliradians of phase noise. I think we can do a lot better than that. And then this other quantum network between Delft and The Hague is a few hundred milliradians. I don't quite trust these measurements. I don't think they're doing them in the right way. No, so that's why I'm here. I'm just going to tell you kind of what I think is the correct way to make these phase noise measurements, and how to actually implement these systems. Okay, so I guess the first question is, and this is what Krister is saying, there's like a lot of interest, like what is phase noise, and how do we actually approach it in the like optical clock community? How do we analyze it? How do we cancel it? So when I say phase noise, I'm talking about um, this this unit, sorry, this quantity here, dBc per hertz. And really all this is saying is like, if I take a noise, sorry, a power spectral density of, the phase, like what are the strengths of the side bands, the frequency side bands relative to like the carrier strength. So that's the C in dBc here. It's a weird convention. It doesn't always make sense, but this is kind of what we use in the clock community. Yeah, so it's related to power spectral density in this way on top here. So what I'm showing you here is, basically this is the phase noise of a fiber. a couple kilometer fiber that we've deployed. And when we don't lock it, it looks like this curve in blue. So you can see there's a ton more noise at low frequencies. So this is 1 hertz, 100 millihertz, and so on. And it's a log scale, right? So there's actually a lot of noise in close to DC. But then there's not that much noise at higher frequencies. And so, but what we can do is we can measure this phase noise and feed back to cancel it away. And what you can see with the orange curve is that we can do several orders of magnitude of phase suppression within the bandwidth of whatever actuator we're using to feed back and cancel this phase noise. But importantly, we're always adding a little bit of noise at higher frequencies that's outside of the bandwidth. But typically, this is a sacrifice that's like well worth making. And just kind of to, if you're wondering, like, where does this plot come from? Like, how are we generating this data? Essentially what we're doing is, we want to know the optical phase noise of an optical signal, right? So, and what we're doing to extract that is we have to interfere it with another laser. So we interfere 2 laser beams that have this noise that we're interested in, and that creates a heterodyne beat note. And we'll detect that on a photodetector and compare it to some other low noise reference. And this is really how we're generating the phase noise, and then finding the the FFT and the power spectral density of that time trace. So that's kind of what we're doing to generate these plots. Okay, and then these phase noise plots are interesting, but I think what's more interesting is what happens when you integrate this phase noise up. And that's what I'm showing here with these dotted lines. So what you can see, and what I mean when I say integrated phase noise, is that I start at these high frequencies. So in this case, a megahertz, and I integrate to the left. So I'm integrating from low time, so short times to longer times. And as I integrate the phase noise, the integrated phase noise increases. And you can see it's massive for the unlocked fiber, and not even visible on this plot for the locked fiber. And we're targeting something like 60 milliradians of integrated phase noise. You can see that for the locked or the unlocked fiber, the integrated phase noise goes very quickly up to tens of radians. So this is you can't use an unlocked fiber. You must lock it somehow. And so this is kind of 60 milliradians is roughly lambda over 100, and it's going to lead to something that's greater than 99% entanglement fidelity. That's kind of the goal. And so for classical signals, like we typically it's important where we start and stop integrating. So we typically integrate like all the way to the Nyquist frequency, or this like f/2. And that can be like quite massive. And we usually have to worry about things like shot noise and thermal noise, things like that, that really don't exist for single photons. So in our measurements, what we're really interested in is not the laser noise that we're using to kind of like probe the fiber, but we're actually interested in things like how much noise is the fiber adding itself without the laser noise. These things are kind of inextricably linked, but we can kind of make good estimates. So in this case here, you can see that the fiber doesn't really add noise beyond a few tens of kilohertz, and so I think it's safe. We can kind of pick an integration start time of a few kilohertz and integrate from there. And then we could flip this diagram around if we wanted to, and instead of frequency, we could integrate over time instead. Okay, so and the integrated phase noise is linked by this equation up here to timing jitter, which is like it's kind of a nice metric to say, my network supports like, femtoseconds or attoseconds of timing jitter. But yeah, we can just convert between the two using this equation here. And so, right, we're targeting kind of this like less than 100 attosecond timing jitter for our network. Okay, I hope that was all clear. No one's asking questions, so it must be super clear.
Can I jump in? I do have a
Yeah, go
question.
ahead.
Yeah,
Yeah.
this is Mike Raymer. Hi. So why is the only phase noise that this measures? Well, why does amplitude noise also not show up in this measurement?
You are wondering why we're not interested in amplitude noise, or
No.
why that doesn't why does that not make it into this measurement?
The latter.
So I'll tell you in I think maybe the next slide, but yeah, there's a usually we like to operate at like away from DC. So at DC, for a lot of these optical systems, amplitude noise is a huge issue, and so we always offset to some kind of like um, some frequency. So in this case, I'm interfering two lasers with different frequencies, and in that way, like I stop being sensitive to amplitude fluctuations. I'm only really sensitive to frequency and phase fluctuations.
Okay.
So that's kind of an important distinction. That's kind of a really important thing to do here if you want to, really stabilize very well. And that's also here in this diagram. So what I'm showing you here is basically all the details of how we take a laser and how we distribute that phase across a fiber without adding extra phase noise. And so it's simply just an interferometer, right? We split one laser into two beams. There's a reference mirror that we kind of hold incredibly stable. And we compare that with light that traverses the fiber. It gets reflected by some end, either a mirror or just the end of the fiber. And so we're just doing this interference measurement here. And what you were asking, Mike, was that like in this case, like why are we not sensitive to amplitude noise? And in this case, what we're doing is we're actually introducing an extra frequency to the light that goes through the fiber. So somewhere along the line, we need an AOM, and this shifts the frequency, and it shifts it actually twice because we double pass this fiber with the light. And as the light kind of makes it back to the sending station, we get this heterodyne beat note that carries phase information only, and we're really not sensitive to amplitude fluctuations, which is kind of a nice a nice thing. It's actually crucial, like if we want to make very good phase measurements. And then, yeah, okay, so I actually had a little box about that. So it also makes it so that we're less sensitive to other DC noise sources. I mean, there's always, 1/f noise in the detectors. They can be quite noisy, and we want to get away from that by going to AC. And things like ground loops are a constant problem. So DC is kind of a horrible place to operate. If you can get away from it, do it. So, and then the other thing here is that, I'm kind of putting in all the details. What are we doing to kind of distribute light in a phase stable way? We might actually need like more than one actuator to stabilize, the frequency or the length of this fiber. And so when we do optical clock measurements, we really are only caring about the frequency of the light that we send. But in this case, like, if we want to send optical pulses or single photons that have some bandwidth, then the total length of the fiber is really what we care about, not just the phase. So we actually have to use some kind of actuator that talks to the length of this fiber and changes the length of this fiber. So we use in this case, we use a fiber stretcher that's very, very fast, but it kind of has a limited range. And so we have a secondary actuator that, is slower, but has quite a bit more range. So this is kind of how we deal with, longer fluctuations in the fiber length due to things like temperature and that kind of thing. And then kind of the final point here that I want to make is that to probe the fiber, there's kind of this there's a limitation based on the time of flight of the photons in the fiber. So that really limits the bandwidth that you can sense these phase fluctuations and then also feedback. So to kind of distinguish between what is the fiber noise, how much noise is being introduced by the fiber, and how much noise is on the laser itself, you need a really noise-free laser to do this. And so, what part of the atomic clock community is, one of the pushes has been to make these very, very low noise lasers to probe the atomic transitions. And so we need to use these. These are basically lasers stabilized to these very nice optical cavities. Also another phase lock. Okay.
Can I
And
jump in
then-
with a question?
Yeah, go ahead.
So as these things get longer, the bandwidth is going to fall. Is there some point where it's to your advantage to break it up in sections and stabilize several shorter sections individually?
Yeah. Yeah. I mean, that is kind of the only way around. Well, that's the most straightforward way around that problem. Yeah, you have to break up the link. And that point is probably at a few tens of kilometers, just based on the noise spectrum in the unlocked fiber. So typically fiber doesn't add a lot of noise past, a few kilohertz. So I think, yeah, so if it added noise at like a megahertz, then we'd be kind of dead in the water. But you'd break up these links at like a few tens of kilometers, I think, for like very excellent phase stability. I think if you're willing to make sacrifices in kind of this high frequency phase noise, you can go longer, but not much longer.
And then just a question, in the very beginning, when you showed the phase measurement that you said you don't understand, you showed that locked
Let's see, how do I get back there?
system. And the thing that struck me was the noise was like half a radian. And
I'll try to get back there. Where are we? Okay, you were talking about this.
no, in the very beginning.
This stuff.
That one. So
Yeah.
that's 470 milliradian. That's half a radian. I would never have guessed that it would be that much phase noise in that locked section. Am I missing something?
So I don't know what this phase noise, does it come from the measurement system that they're using to measure the phase noise, or are they just kind of, is their feedback so slow that they're not able to fully suppress the noise? I don't know.
Okay, because I would have thought like in the section where you see full 100% modulation, that would be something like 1 radian or something like that. And
100, what, sorry, now what are you talking about?
that the partially stabilized or the unstabilized, you see variations of the optical density varying by 100%. So
You were talking about this?
no.
Like just on the, I see,
Yes,
partially
yeah,
stabilized, unstabilized
right.
on the left. Okay, yeah.
Right. So yeah, and that even says it's 2 radians as the
But
sigma.
sorry, jumping in, it's per second, right?
Oh, it's per second.
It's per second.
I have to think about what that means, but okay.
Yeah.
Right. I
So-
think the standards here are like not quite set. So yeah, I also don't quite know what radians per second means in this context.
Okay.
it could be a drift
Mhm.
of the phase. I mean, maybe you can interpret it like this, but don't know.
Okay. Thanks.
Okay. All right. Okay, where am I? And so I don't have a ton of time left, so I've kind of described to you how we do classically this phase stabilization, but what we're actually interested in is like making this quantum compatible. And so we kind of do the same thing. We do the same phase stabilization with a classical laser, but we have to introduce some kind of way to distinguish between like our classical channel and the quantum channel. And the way that we've chosen to do this is with, like time multiplexing with choppers. And so, what we're doing is chopping up the probing laser, and then, we have this anti-synchronized chopper that's kind of catching any stray classical photons, and so that kind of leaves a channel for, or these kind of windows in time for the single photons from the other side to kind of make it through the fiber and hit our single photon detector. So that's kind of our scheme here. And so what we've kind of measured a few things to kind of show that this is actually working. Can we kind of stabilize things, and can we kind of make it a viable?
Sorry, Dick, can I interrupt for just a quick
Yeah.
second? So,
Mhm.
I think there's quite a bit of interest in the stabilization technology, especially from folks in the quantum optics community. So, because of the great discussion, I want to keep that going. What I propose is that I know some folks have to leave in a couple minutes, but that we kind of keep this going for another like 5-10 minutes after past the hour. And this recording will be on YouTube for anybody who has to leave now but wants to catch it later. And also on our website, you can check it out. So Nick, we'll give you a little bit more time for this.
Okay, that's great. So I can continue, or people can kind of like ask questions on what I've talked about so far. Okay, if not, I will.
Hey, could I just ask a very quick question, because I think I've got to go.
Yeah.
So your 100 megahertz feedback with that fiber stretcher, that
Mhm.
that fixes the problem in the low frequencies, kilohertz to 100 megahertz. Is that the idea? You're getting rid of this low frequency noise.
Yes, I mean that's what the stretcher is doing. It's sensing like all of the noise on the fiber, and it's feeding back to correct that. What
Yeah.
what the AOM is doing is it's shifting that signal so that now we're not sensitive to laser noise.
Yeah.
Yeah, and that's the key here, because if you imagine if you didn't have an AOM in this and you were doing like a side of fringe locking, which I'm pretty sure that in that first slide that's what they were doing. You're sensitive to phase noise, but you're also sensitive to the laser power drift, right? Or other sources of power drift, like coupling into single mode fiber and that kind of thing. So this is a crucial means of kind of getting away from those DC noise sources.
But then you want to send light at a much higher frequency with much higher frequency information on 50 gigahertz or 100 gigahertz or something, maybe doing phase measurements of that. Are you saying that when you correct for the low frequency noise here, that the high frequencies you don't have to correct for because they're so small?
So yeah, I mean there
Right.
is a bandwidth to all of these feedback actuators, but what we're really kind of tailoring that bandwidth to is how much noise is inherent in the fiber. So let me kind of go here again.
Is that
You can see that like there really isn't that much noise, in the due to the fiber past maybe 10 kilohertz or so, right? So that's just fluctuations that the fiber adds because of vibrations and acoustics and temperature drifts, right? So if you do have like systems that operate much faster than that, that's okay. Basically, these noise sources won't affect, shot to shot, pulses or single photon phases, right?
Okay, I'll leave my question at that because I do have to go. Thanks so much.
Okay, sure. Okay. Let's see. It's past 10 now, so I don't know if I guess okay. If there's no more
Keep
questions,
going.
I'll keep going. Yeah. So I was talking about, how we're distinguishing classical and quantum channels here. And what we've seen is that, while everything is stabilized, we can get this very nice kind of isolation between the two channels. And like this is co-propagation. So this is a single photons traveling alongside, hundreds of microwatts of classical power. And so the chopper kind of does most of the heavy lifting. We've also kind of employed a few other techniques to kind of get this isolation down further. So, temporal gating. So that's like, when do we expect the quantum photons to come in? We also use, you can see the quantum is at one frequency, the classical is at another. We can actually use that as well to suppress some of the the leakage from one channel to the other. And okay, so I wasn't sure if I was going to show this slide, but this is kind of like the full like detail of what we're doing. In our experiment, we have actually these two stabilized paths that are stabilized independently. So the kind of stabilization laser feeds both of these fibers, and they're both stabilized independently. As part of a network, these fibers would kind of go to other nodes, but in this case, we're just using it to characterize, how well we're able to cancel fiber noise in a system like this. Okay, so I'm gonna move on here. So what we're interested in is like, not only like the phase noise and the isolation, but then how like indistinguishable are these two paths in terms of like, polarization, dispersion, attenuation, things like this. And so what we've seen is that and this requires stabilization to get a plot like this, but we see basically, much higher than 99% visibility of these two paths as single photons traverse them. So really what I'm measuring here is, I've stabilized both of these paths independently, and now I have single photon level states coming in and kind of being split between these two fibers, and they are being collected at the other side and fed into a single photon detector. So, and then I'm kind of making these fringes by varying a piezo stage in one of the arms. So that's what we're measuring here. Basically, very indistinguishable path lengths over many kilometers. And then the kind of the last metric is actually how well are we doing with the phase noise? I told you like we're adding a chopper and we're going over several kilometers. Like all of these things kind of degrade the phase noise. And so what I'm showing you here is that if we don't chop, this bottom purple curve here, we actually get the best phase noise. But we kind of actually need to chop because we need to do this classical quantum isolation as well. And so we have to add some amount of chopping. And what we're really interested in is this integrated phase noise, or this, I've kind of scaled it also as timing jitter here. So, chopping is like adding a little bit of noise. But what we've seen is that we can do pretty well with choosing the right chopping speed. So we're 6 kilohertz or so, we're less than 100 attoseconds and that's like for quite a long time. So we can actually, what this tells us is that we can make measurements for, you know, seconds or tens of seconds at a time, and be demonstrating like quite low timing jitter. Okay, I don't know if I want to talk about that. Well, okay, maybe I will just mention this, but there's a right way and a wrong way to do phase noise measurements. I think a lot of people do what I call in-loop measurements. So basically, you're measuring what is the phase noise that the feedback actuator thinks that it sees. And that's not the same as the actual phase noise in the system. So what you have to do is basically, and we can talk more about this, at some other point, but an out of loop measurement actually takes the phase that you've sent across a fiber and compares it to the original laser. We call this a loop back measurement because we've kind of looped back a fiber on itself. This is the right way to do a phase noise measurement, and it kind of tells you how much phase noise is actually in the system when you transfer over a fiber. In-loop systems are always in-loop analysis is going to underestimate how much phase noise. So yeah, I think that's what a lot of these groups are doing. So that's not the way to do it, though. Okay. And then with the last few minutes, I don't know how much longer we want to spend on this stuff, but as kind of like a higher level view, like if we're able to stabilize these links between network nodes, we also need a means to distribute kind of a phase across the whole network, kind of a common phase. So, in this technique, we're using some CW laser to probe and stabilize these optical paths. But there's also some leakage of the CW light into the node, and that can be used to actually as a signal to actually synchronize these nodes together. So, and we know how to do this for something like a frequency comb. Imagine that these the SPDC sources are pumped by a mode lock laser that's stabilized as a frequency comb. We can use the CW light as a phase reference to phase stabilize everything together. So that's kind of like the high level view of a bunch of nodes together, and we kind of need everything to be below lambda over 100 phase stability. So this is kind of a tall order at the moment, but we're kind of inching towards this. And then if we have there, we want to introduce other elements into this, such as like these cavity-based quantum memories and other things like that. They're all going to require this phase noise suppression, because they're all sensitive to it. Okay, and then I have just this slide of like maybe helpful resources. I mean, we do all kinds of phase stabilization for optical systems in the atomic clock world. And people have spent decades on this and won multiple Nobel Prizes. So it's worth looking into some of these things for, and I think it's kind of quite useful to port some of these things over to the, these quantum systems. Sorry, I keep getting messages. And okay, I think I'm going to stop there. 10 minutes over. I'm sure I could talk like infinitely about all this stuff, but maybe there's like some time for extra questions here.
Nick, I had a quick question on the chopping. If you could remind me, does the duty cycle change, or does that remain constant for this?
So the duty cycle does not change.
Okay.
For these measurements, I'm just kind of upping the speed.
Okay, so this would be like a 50-50 duty cycle?
Yeah, so that's an interesting question, because it can be kind of what we want it to be. So in this case, what I'm doing is I'm chopping at 50% duty cycle with the first chopper, but I have this anti-synchronized chopper that's actually not, it's actually set at 25%, I guess, 25% air. So it's actually, there's some room on the sides for, some kind of mismatch in synchronization.
Okay.
If that makes sense. It does
Yeah.
it does mean
Yeah.
that we're killing quite a bit of the quantum signal, but
Right.
it's kind of it's the way around for deployed systems that exist today.
Sure. Yeah. And I guess, yeah, there's optimization that could be done over that. And yeah, that's awesome. Cool. Okay. Thanks.
There's a question from Duncan, and the um, he says, really nice results. Are the 2.1 kilometer fibers deployed or in the lab? Reason I ask is because I was wondering about temperature effects, because the CW laser and the quantum light are different wavelengths. Do you expect to see temperature dependent dispersion?
Yeah, so well, first off, they're semi-deployed. And so when I say that, I mean I take a fiber and I string it down the hallway several times and I bring it back to the lab. So it's not actually going anywhere, but it is like going through a very, very noisy environment. And what we see is actually this fiber, this 2.1 kilometer fiber actually has more noise on it than the actual deployed fiber. So we have a fiber that runs from NIST to the university, and that has less measured phase noise than this one does. So I think that's kind of it's a nice test case. And yes, I was also wondering before I started this if there was going to be a difference in, can we adequately stabilize with one color for another color? And I think the answer is yes, because we've done it. But we haven't fully characterized, how much extra noise is this adding? This is still kind of like how far can we go? If they're on, different. Yeah, I mean, yeah. So okay, so it's a question that I don't quite know the answer to, but I think we've been able to do good enough with different colors that are kind of close together.
And then Joe Britton has a question as well. Joe, do you want to just unmute and ask your question?
Sure. Yeah, thank you for the great talk. I have a bunch of questions, but the one that was in the chat is just whether you're using track and hold for your PID for the fiber stretcher. It wasn't indicated, and it looks like your chopper is just an analog chopper. So,
Yeah, so we are doing we could be doing something smarter and probably getting better results, but what I'm doing is I'm actually taking I'm basically just limiting the feedback bandwidth based on the chopper. So I'm chopping at 6 kilohertz, which means that I can't I have to make it so that the feedback algorithm doesn't see changes faster or on par with 6 kilohertz. So I limit the feedback bandwidth of the PID controller. This is an FPGA based servo, so it's we kind of have quite a bit of control over it. So I can limit the bandwidth to a few kilohertz. So that's the answer. Basically, we're kind of doing it, not really doing a track and hold, but we're just limiting the bandwidth so it can't respond faster than the chopper is chopping, if that makes sense.
okay. Yeah, if this is the Librant feedback box, I think it has track and hold that you can use.
Okay. Yeah, so I'm using a different, we have a FPGA expert here that is helping develop these systems. Haven't used the Librant box.
So I have one other quick question. You showed this really nice interference on slide 12.
12. Yeah, okay.
About polarization stabilization. And so a sort of question in my mind is, you are controlling the path length of the fiber,
That's right.
but at what polarization, for what polarization state? you were to send in a different polarization, you'd find that the propagation delay is now different. And so you'd have stabilized it at one polarization, but not the other.
Yeah, so this is also something I worry about for longer term measurements. And, in fact, like I got these results without really having to worry about the polarization, but the polarization should matter. So I think what we're doing to kind of deal with this is to just put, polarizers. So we're selecting for a specific polarization. And then if we want kind of high throughput in some like in the real system, we're going to have to control the polarization actively. And I think that it adds complexity, it adds cost, but it's not something that can't be done.
So I would have thought in slide 12 that your standard deviation would be varying as a function of measurement time as you accidentally drift into and out of a high count rate, because you're
High count rate. So I mean, so you're
cutting photons because they just aren't the right polarization state because you're not controlling the.
I see. So we are using. I mean, it depends on the system that you are like the fiber you're sending through. So the fiber we use is kind of this nice armored fiber. It's actually meant for snaking through like conduits outside. It's rat proof. It has like a nice like big metal jacket. And that holds the polarization pretty constant. And so, and it's also not like on a telephone pole, like waving around. So that's, that's a bonus. But I think the polarization is pretty stable in these systems, kind of all by itself, passively. But yeah, I think for longer term measurements, it would change. So on a day-to-day basis, it might change. So I think in that case, we would have to implement some kind of like, feedback or something.
Yeah, I guess following on that, Nick, have you made measurements on the polarization, like the polarization stability? Because we're doing that right now in our group, but over a shorter fiber length, about 300 meters. And passively, we see very little drift, but there is some. And it's on a time scale of, well, Matt here, he was on here, I don't know if he still is, but it's on the order of maybe minutes or so.
Mm-hmm.
Yeah.
Yeah, I mean that's definitely possible. I can imagine that there would be some polarization drift here as well. If we were to kind of go for hours at a time, maybe we would start to see
And I guess
peaks drop.
Does your feedback, like you're stretching or squeezing the fiber, does that introduce a little birefringence at all?
Supposedly that's what I've heard, but I mean just from the measurements that we've made, I don't see it. Like it,
Okay.
so I mean, I think that the fiber itself is, and Krister also uses this. It's not this type of fiber, but kind of a different version that's very polarization stable, kind of nice jacket. I think is important for these measurements. Yeah, so I mean, we see actually very bad results if we just use kind of the 900 micron jacket. It's just not insulating enough. So you need something with like an adequate jacket. For sure.
Okay. Good to know. All right. Thanks.
I think in the interest of time, we'll wrap it up there. I also want to just mention, so Joe Britton, who is talking and asking about the initial question about polarization stability, him and his team have some really nice results in modeling software for really understanding polarization effects in fibers. So I strongly recommend if you have polarization questions, you talk to Joe and his folks. So and just want to say thank you to everybody who came and stuck around. We'll make this recording available on our website shortly, and we have another tutorial coming up in 2 more weeks.